So good morning, everyone. For those of you who are in Europe, and good afternoon for those of you who are in Down Under. So we are here with our guest, which we are very happy to have, Micheal Hush, lead quantum control engineer at Q-CTRL. He accepted our invitation to talk about the commercial software development for quantum control, and also delve a bit in the topic of moving from academia into the startup world, which is something that is getting really actual. And so, thank you very much to be here. Micheal, the floor is yours.
Okay, so yes, my name is Micheal Hush. I'm the head of quantum science and engineering here at Q-CTRL. So today I'll try and share my screen. Today I wanted to give a bit of an overview. There we go. Is everyone still hear me? Yeah. So can I get a yes from one person saying that they can see Q-CTRL right now? Cool.
Yes.
Okay, we're good. So one other question I had is, how long do I have? I'm happy to also answer some questions at the end. Should I go for 30 minutes or so, or?
Yes, if you wish, you can go also longer than that, but as you prefer. Normally we do up to 1 hour presentation and then questions, but you can be shorter. I mean.
I'll try and go a bit shorter to make sure I've got some questions, because it is, I wouldn't mind hearing some questions about transitioning from academia to the quantum industry. It is sort of an interesting topic, but it's hard just to present on that. So I'm happy to take questions at the end around that as well. So today, I wanted to give you a bit of an introduction to who Q-CTRL is to start with, just as who we are as a company. And then I wanted to show you it's going to be a little bit different to maybe what you've normally seen. It's not going to be as academic. I'm going to give you a little bit of a demonstration, or just show you how the software actually directly integrates with some of the public quantum computers like IBM Q, and then give you some results of our quantum control solutions working on their devices. But if you want to ask any questions about the technical detail, there's two options. If you're shy, you can actually read the manuscript, which I'll highlight at the end, which has all the details there, which you're welcome to have a look at, or just speak up as we're going along, and I'm happy to dive into any of the details about how we actually develop our controls and the physics behind it. But I'm going to try and keep the physics kind of light and focus on some of the results. But I'm happy to dive down. Just know that I'm not talking about it not because I'm hiding anything, just because I'm trying to keep everyone's attention. And sometimes maths can get a bit boring. So to begin with, Q-CTRL. So Q-CTRL, we're a startup. We're entirely venture capital funded. We started in Australia, and down here we have some of our investors. Main Sequence Ventures is actually an Australian venture capital fund, which came out of there's this publicly funded thing called the CSIRO in Australia, which handles a lot of technology. And they really saw that by putting venture capital into the sort of deep tech industry in Australia could lead to some real great innovation. And so Q-CTRL was one of their initial investments in the quantum space. So the professor and our CEO, Michael Biersick, was at the University of Sydney. He's had a history of working on quantum control and cold ions. And he basically partnered with Main Sequence Ventures to start off Q-CTRL. And since then, we've kind of expanded. We now have venture capital funding from both the US and Australia. Some of the key ones are highlighted here beneath. And also the Asia Pacific region. And we now have offices in both Sydney and LA. So what do we do? So as a company, our aim is to become the trusted source of quantum control for all people looking at building quantum technologies. And so we develop novel quantum control techniques which can help you both identify what's going wrong with your quantum device and then improving its performance. And we deliver these solutions through software infrastructure and also services in terms of integrating that software into your hardware. So we have a variety of customers already. We work closely with IBM, and I'll show you a lot of the results that we've been developing on their devices. We also have a close partnership with Rigetti, and we also help new startups like Bleximo, who are building new superconducting devices. We have a variety of academic partnerships as well. Some key ones to highlight, of course, with the University of Sydney, where my CEO, Michael Biersick, still works. And we also have established new collaborations like with the Australian National University in the quantum sensing space. So what's a little bit different to us compared to some other startups is we have a really good balance between people who have like studied quantum control in a very technical sense, and also people who are designing and making new products. So half of our company, which is under my division, have a background in quantum control or machine learning. They've done a PhD on the topic, so they've developed new optimization algorithms or worked with specific devices. And then the other half of our company has a background in developing products online. And so they have a lot of experience on making reliable software which is deployed online through cloud infrastructure, which is easy to use and efficient. So kind of between those two sides of the company, we think we work well together to create a product which is both interesting and engaging, and also like has that technical ability to solve problems that people are facing. So initially, Q-Control, we started working in the quantum computing space just because there was, of course, a lot of interest in there, a lot of investment. We recently secured a Series A funding round last year, which has allowed us to expand. So we also are now looking at quantum sensors and which have like a variety of applications in defense, etc. Today, I'm going to mostly focus on the quantum computing side of things, but if any of you are interested in cold atom sensors or applications of control in that space, feel free to ask me a question at the end and I'll highlight some of our work there. So then, how do we actually deploy these solutions? Well, we do this through a variety of products, and these products are available online and are delivered through the web. So our kind of most accessible product, if you're new to quantum control, you want to have a visual experience of learning how it works and how it can improve quantum technologies and quantum computers. I'd recommend having a look at Black Opal. You can sign up today for free and have a look and play around with it. It gives you some great visualizations on how control works. For those who are interested in developing algorithms for quantum computers and just want to get the maximum performance for them, subscription to say Rigetti or IBM machine, we have a new product which will be coming out around the end of the year called DevKit, which is really targeted at getting an algorithm and just abstracting away all the details of that device that you're using and getting the best performance you want. But today, I'm going to talk about our current product, Boulder Opal, which was just recently introduced to the market. It's really targeted at people who are developing the newest in quantum control techniques or R&D professionals at quantum technology companies who are working on the hardware itself. So it's a software package which is designed to be basically, it's a tool for analyzing quantum control, or it can be a tool that's integrated into your quantum technology itself, into its automated optimization and improve its performance. So the underlying physics that we really use and deploy in these techniques is the idea of designing control which is robust to errors. So we provide tools which not only allow you to figure out what's going wrong with your system, but then once you understand what noise is in your system, you can then apply controls, basically drop-in replacements at least for the individual gates in your quantum computer, which are robust to those noise processes. So in order to do this, we have a variety of tools to help develop these robust controls. First, we have a control optimization package. So given any description of your quantum computer, its control lines, the particular qubits you're using, how they're connected, we can provide a variety of optimizations to produce you robust controls which do the operation you're targeting in a manner that's robust to the noise in the environment. We have a variety of tools for basically evaluating the performance of those controls. So we can tell you, we can simulate quantum computers, we can simulate them with a variety of realistic noise processes, which are either white or colored. And we also have tools for basically summarizing the quality of a control. This is the filter function package, which I'll briefly get back to in a sec. And lastly, we can actually characterize what's going wrong with your hardware. So we have tools for using the qubits as a probe and measuring things like parameters in your Hamiltonian, and also the noise spectral density of noises in your system. So you can figure out what noises are there and potentially where they're coming from by looking at their noise fingerprint, so to speak. So just finally, a brief overview of the benefits you're expecting. So these controls, by using our controls, you can suppress hardware errors. So if there is noise in the system, you can drastically reduce its effect on the quality of your performance of your gates. And then the key thing, which I'll come back to later, is that by using our controls, which are robust to noise, you can homogenize errors across your qubits and in time. So you can make the performance of your worst qubit and bring it up to your best. And you can also homogenize errors over time. So you can ensure that your quantum computer works more correctly in between times between calibration runs. Lastly, I guess one of the key things that is often brought up if you're talking about errors is error correction. So error correction is still very challenging to do on the scale of quantum computers we have today. In the long run, of course, you have to have error correction to get everything to work. But nevertheless, the control techniques we're talking about today are kind of the lower level thing that you might be able to do right now to get around errors. So they're kind of targeted at NISQ computers, near noisy intermediate size quantum computers. But what you'll find also that if you can use these same controls to actually decorrelate noise processes and improve the performance of your error correction as well. And there's an archive paper here, which I'm welcome to have a look at. I can link anyone who's interested afterward as well. So today, that's sort of a quick overview of what Q-Control is and what we do. So now I'll go into a demonstration. Well, I'll give you a look at our product itself. So if you go to, there we go, cool. So hopefully everyone can see the screen now. So if you go to app.qcontrol.com, you can sign up today for free and play around with everything I'm going to show you. There is this Black Opal product, which I mentioned before. It has some nice visualizations of qubits and running operations on a quantum computer. So you can see the dynamics. Oop, that was a surprise. Nothing better than a live demo to get an error coming out. Let me just double check, just refresh that. There we go. Okay, the visualizer is getting an error, but I'll report that after this talk. Let's go back to the one I wanted to show you was, of course, Boulder Opal. So Boulder Opal is our package. It's a Python package, which you actually install in your machine normally. So you simply go pip install Q-Control, and then you would integrate this package into your actual automation process itself. But today I'm going to give you a look at one of our application notes. So what we've done here is when you sign up to this app.qcontrol.com, you can log in and have a look at all of these notebooks, which are interactive and executable. So this notebook was what I'll briefly go over today. It's on superconducting qubits, and in particular with the IBM machine. And it shows how you can actually improve the performance of single qubit gates using our optimized pulses. So the things I really wanted to highlight here is that everything in this notebook, all the code is there for you to look at, and it also has all of the actual code that you would use to run this on IBM's machine. This particular version of the notebook can be used. You can sign up for free with our account, get a 30-day trial, and you can also sign up for free with IBM to get access to their particular device, RMOC, which has their open pulse design, which I'll come back to in a sec. So you can actually, for free, at least test everything that's in this notebook and execute it yourself. So let's go to the beginning. So what we're going to talk about today is basically optimizing a NOT gate. So I'll go into some additional detail in a sec, but we're going to consider the quantum computer, one of the quantum computers available at IBM. So normally at IBM, when they initially released their code, you could only program algorithms using gate level control. They recently opened a package called OpenPulse, and OpenPulse allows you to program the actual pulses themselves. So you can control the microwaves that hit their superconducting qubits and change their phase and amplitude. And this allows you to do more sophisticated control where you can see what Q-Control's robust control techniques can achieve. So to use their package, to use our package, first of all, you need some description of the system that you're trying to solve. So today we're going to look at an individual qubit, and we're going to consider making it robust to a dephasing process. The Hamiltonian of our system is going to be basically this Hamiltonian. We're going to have a control part. The control part is the microwave drive, which creates an effective Rabi rate. We're going to assume that it is driven with an IQ modulation, so we can independently control an I channel as a function of time and a Q channel as a function of time of the qubit. Then we're going to assume that there is some slow varying noise process. To start with, we're going to look at just a dephasing process. So we're going to assume that there's some random constant which is generated here, which creates a small sigma Z drift. And later on, we will consider a different type of noise source, which is if there is a small random noise process associated with a miscalibration of the Rabi rate. So basically, your microwave drive happens to be misaligned. To start with, let's just consider this dephasing process. So what you do with the Q-control package is once you've written down a description of your system, you may also use our other tools to identify what the parameters are in the Hamiltonian, but today we're going to assume that at least you've identified what your Hamiltonian is. Then you simply write down into our notebook what these parameters are. So you tell it, this is our Hamiltonian. So this is our control operators, the sigma x and sigma y. So we describe the system with a series of commands. We create these I. This I is basically our control for our I thing, our I operator. And in particular, we can give it a variety of different constraints which are relevant. So we tell it the duration, the number of segments that is in that pulse. We can also include a total mixed fixed modulus and a total upper bound, so the maximum Rabi rate you can hit. But the key thing I wanted to highlight here is what we're going to do here is consider two different types of pulses to highlight that implementation is really important. And we're going to do one pulse which has the difference between the segments, so basically the slew is bounded, and one where it is not bounded. So once you've set up your system, you've defined your Hamiltonian, you've set up a variety of controls and told our package what's what, then running the optimization is as simple as... here's the actual command. So when you actually run the command, the optimization is as simple as Q-control run robust optimization.run. So what happens now is the optimization package we have runs a variety of control optimization problems. We do a hybrid cost function, which both minimizes the fidelity of the infidelity of the operation. So we calculate the final fidelity given that Hamiltonian and ensure that it does the correct operation. So here we're trying to create a NOT gate. So as a total, it needs to go from the top to the bottom of the block sphere. And then we also ensure that the pulses we design are robust. And we do this using a filter function framework, which I can give you more details about at the end. But effectively, we integrate the noise operator in the frame of the control, and we ensure that that operator goes to 0. So it's sort of like ensuring that as you move along the path of the control, that if there was some type of noise process there, that there would be a self-cancellation, because the shape of the control you're doing will go, the noise applied will basically cancel itself out on that path. So it's sort of like in a dephasing case, it looks a lot like designing an echo into your pulse, but because you can define a completely arbitrary operator for that noise, it won't always pick an echo. If you have a different type of noise process, it will take advantage of some other trick. So
May I ask a question?
Go for it.
Yeah, so you talk about cases where you know what the noise looks like. So you say you have an operator for your noise. What about cases where you don't know what the noise looks like in a given experiment?
Yeah. So if in order to get an advantage from the techniques we're talking about, you need to have some knowledge about the noise that you're dealing with. It's not like error correction where you're attempting to use your measurement projection to project it into a particular case. The control techniques we're talking about are often relevant where you've made the device as best as you can, but you might have still some dominant process. It might be a dephasing process or an amplitude miscalibration. So we do also have tools. Where are they? User guides. So we have noise characterization and reconstruction features. So these allow you to basically send a series of probe pulses, which you can check to see if that noise happens to be there or not, and use the qubit as a probe. But you still have to do some kind of technique to identify if the noise is correct, or you have to have some type of physical understanding of your system to identify that there is a noise present. We are doing other we are investing in other things as well. So we have some other work at looking at machine learning techniques to kind of automatically optimize these systems. But we still feel like there is a place, and I'll show you some of the success we've had with this approach, but there is still a place for developing controls when you have a detailed understanding of the Hamiltonian, I would say. Does that answer your question?
Yeah, absolutely. Thanks.
Yeah, no problem.
Could I ask a quick question? Sorry.
No, I love it. This is so much better. I love questions. They make things much more interactive. Go for it.
So I just wondered, I think from what I remember, you're doing like reverse mode automatic differentiation. Is that correct? From what I remember from the like original paper, you guys said like you were using TensorFlow to like take the gradients without having to define exact gradient functions.
Yeah. So we like that approach because how much do I want to go into this? So we have a variety. Okay, so basically we use TensorFlow to write down a map of how your controls relate to the final fidelity that you're achieving. Then we take advantage. So TensorFlow has a lot of use in machine learning, and one of its powerful capabilities is the ability to analytically create a gradient given a map that's been created. So there's not, if you're just looking at grape, and these results look somewhat similar to grape. There is the additional. This is a little bit different to grape in the sense that you've got a bound slope, but still grape kind of lives close to this result here. But if we go to control hardware, so what we've also added, particularly with superconducting qubits, they tend to have significant bandwidth limits, and they have kind of quite complicated constraints. So we've also looked at creating optimization tools which can take into account a filter. So you can actually define arbitrary linear filters for your system. And in fact, you can add arbitrary nonlinear maps between whatever your actual control pulse is and what hits that qubit. And so that's the power that you gain from TensorFlow, is that instead of having to rely on, instead of having to analytically derive the gradient for every possible operation that would exist, we just allow the user to define their map how they want, and then TensorFlow does our heavy lifting for us. So yeah, that's the current status quo. And we're seeing quite good performance compared to some other techniques out there. There is a lot of interesting work, of course, in the literature around different gradient techniques and how to use them. And we're always keeping an eye on all the results and what we can, possibly employ and not. But currently, we've found that this works quite well for us.
Okay. Thank you very much.
Any comments or questions around that?
I don't think so. We can get going.
Cool. Let's go.
Morning.
Sorry, Michael, actually, Federico here. I have a question if you can hear me.
Yep.
So this is regarding optimizing both for the pulse fidelity and for reducing the effect of the noise. So you're saying that you're using the filter function formalism to do this. So is there any way in which you can include the filter function formalism, the effect that the noise has on the pulses themselves?
We can. Okay, sorry. I think the filter function framework. I don't know how to answer your question. I still don't quite under this. So what is the filter function framework? You just have to assume that your noise process is small compared to your control Hamiltonian. And then there are lots of different approaches for designing robust control, and I don't want to be specific about which is better or worse. I would say a nice feature about the filter function framework is once you pick a noise spectrum density, and in these cases, we're just considering the case where you have largely low frequency, so you can effectively approximate it by just looking at the zero frequency component of your filter function. Then that ends up being a deterministic addition to your cost function. So you can do a deterministic optimization process to get a control which is robust to a stochastic noise process, which is nice in that you kind of know, it's just you don't have to worry about sometimes stochastic optimization can be a bit of a finicky headache. There are, of course, really promising results using stochastic optimization as well out there in the literature, and that is another technique which we have been thinking about as well as an additional feature. But for today, I'm largely just going to talk about the filter function framework. So what was your specific question around that?
Yeah, so I think my point was that you need that assumption of small noise during control, right, for the filter function to make sense.
Yes, you have to assume the noise is small. You're considering, and it allows you, once you assume the noise is small, it allows you to do this Magnus expansion, and then you can treat. Then it's easy to treat the. It simplifies the expression so that you just have to look at the control operator in the frame of. Sorry, you just have to look at the noise operator in the frame of the control when you're designing the robustness property. If you want to go beyond, so there's a trade-off there, of course. You really want your quantum computer to have a small amount of noise, so it's not crazy that assumption is something you would want to be valid. But it's true. I certainly would agree that if you're in a situation where you have large noise, you're going to need something more like a stochastic optimization technique.
Okay, thank you.
Yeah. So back to the pulses. So we've created a set of pulses. Hopefully that gives you some insight to the optimization algorithm. Then we have some neat tools to help you verify that this is actually a control that works, because at the moment it's just a bunch of lines. The first thing we have is, of course, just the classic Schrödinger evolution simulation tool. The key thing, I'll show you the three solutions just clearly. So the first is this unconstrained, and when I mean unconstrained, I effectively mean the bandwidth, because the slew is not bound. So this is one robust control solution where you've got the I and Q modulation shown here. We also have a bound slew, so we're bounding the difference between each segments, and this effectively looks much smoother. And then we have just a benchmark, so we're just considering a square pulse, which does the same operation over that duration. So now we come to the simulation. So we're trying to do a NOT gate. You can see that all three of our pulses effectively change the population of our 0 state to 1 and vice versa. So they're all achieving a NOT gate in the ideal situation where there is no noise. But we can already see that the unconstrained approach does so in a bit more of a varied way. It does 2 repeats, while our bound slow tends to move there a little bit smoother. In order to, these just show that the correct operation is achieved with no noise. Of course, the key thing we're looking for is robustness. We have 2 techniques for quantifying robustness of a control. Let me just make this a bit smaller. So the first is our filter function technique, which I mentioned before. The filter function gives you an idea of how much noise gets through, let's say, to the final infidelity as a function of frequency. So we can see that this black line indicates the square pulse. It basically lets through all low frequency noise, and then noise above the Rabi rate of your qubit starts to be automatically suppressed by some type of self-cancellation. The unconstrained and bound slew results, we can see both suppress low noise frequency. So we expect these controls to be robust to low frequency noise. So this diagram is only valid under the assumption of small noise, but we can draw another diagram which is valid for any noise size. So we can just do a Schrödinger style simulation and turn on a basically static noise. So it's like examining a slice here, and sort of in the other way, where we're increasing the amount of noise. And so you can see that the robust controls remain flat for a significant amount of additional sigma z detuning when added to the system, compared to the square pulse, which rapidly diverges from the correct final state as you increase the amount of detuning. So now that we have these results, let's check that they actually work on an IBM machine. So the fun thing about working with hardware is that absolutely nothing is calibrated, which is a process. So what you actually do on the IBM device is you program, they're just dimensionless numbers between 0 and 1 for your I and Q drives. And then it's up to you to determine how those dimensionless numbers relate to the Rabi rate, which then allows you to do pulse shaping, etc. So we've continued to do a lot of work on how to calibrate, and we'll have more results on this coming out in a manuscript soon. But for this result, what we did is we simply did a scan. So we did a series of Rabi experiments. I'm only going to briefly show you the final result, but basically every single point on this plot is a Rabi experiment where we fix the total amplitude, so basically set the Rabi, these hardware values between 0 and 1, and then we increase the duration of the time, and we looked at the frequency of the oscillation that occurred with the qubit. So here you can see this connects, basically, we measure the Rabi rate at each point, and we can see that the hardware input goes between 0 and 1, but it's not completely linear. There is a linear region to about 0.5, and then above that, there it begins to get this nonlinear curve. So we actually use an empirical fit here. That's the tool we use to then translate. So we can use this result to translate our dimensionful optimized pulses, which have a Rabi rate, and turn them into these relative numbers which you program on IBM Q. I think in both cases what we did is we try to keep it around the linear regime, so around 0.5. One thing to highlight before we keep going and show you the real results is that everything on the IBM devices, in particular ARMOC, which is the publicly available one, which we're looking at now, they reduce the maximum Rabi rate that you can achieve, so they kind of limit the speed of the pulses compared to their ideal devices. So some of the results you see here are relatively slow compared to the real one, but we've since been able to do a lot better on their other device, Valencia. Okay, so with this translation, we're now able to translate the dimensionful optimized pulses into their IBM ones. So we can now do an experiment. The first obvious experiment to look at is just see the evolution of the qubit as a function of time and compare the different pulses that we looked at. So as a benchmark, it's important to note that the IBM device has a relatively significant span error. So even when you do a square pulse, you can see that when you try and do the measurement at the end, the pulse shape is relatively good. It's just there tends to be this constant offset. This is possibly to do with a preparation error that they have or otherwise, but it's important to remember that this is about the best quality result that they get. And then if you look at our bound slew result, where we bound effectively the bandwidth of the pulse, it has a quite comparable performance compared to the square pulse. So it matches the data relatively well. But we can see that our unconstrained version, which doesn't have that bandwidth limit, has quite a significant divergence, and the simulations actually don't match particularly well at the end of the pulse. So we see a hint here that you do have to take into certain constraints when you're actually designing your pulses in order to implement them normally on superconducting qubits. These techniques have all been shown as well in cold ions, which tend not to suffer from these issues. So it does sort of highlight the different issues you face when you try and switch between different quantum computing devices. So the key experimental demonstration, which is just public in this notebook, is a robustness scan. So here, I've mentioned this before. So what we're doing here is we're looking at the real device, and then what we're going to do is turn on an artificial noise. So along this zero axis, we of course, we can control the pulses, so we can also add a detuning to the pulse. And we can see that if you start to detune the pulse that you send down, if it's a square pulse, it does do significantly worse. You quite quickly do not prepare the correct final state as you add the detuning. We couldn't do the scans, but basically we also present the IBM Default Gate. So this is basically their default gate that's available on OpenPulse when you run it. Again, it does well when there's no noise, but as I turn on the detuning, it will tend to diverge away. The unconstrained one is just a mess because it was not implemented correctly because it doesn't have this bandwidth limit that ends up being important. But we can see that the bound slew version on IBM Q does a remarkably good job. And so it remains robust to the noise as we turn it on. So this is kind of going to be a key conceptual plot. And it was our first good evidence that the pulses that we are creating are robust to noise. There are a few critical things that we need to kind of do more on, which I'll show you results on in a sec. But the key things being that the noise here is artificial. So we are injecting this noise into the system. But again, because it's injected, we know for sure that it is actually robust to the noise process we're looking at. And then the other thing that is important here is that at the moment, it's very difficult to discern which particular pulse is performing well at this zero case when there is no noise. And so that's because of a measurement, basically a measurement span error, which allows us not to do a very good job of checking the difference between the ideal pulses and our pulses when there is no noise. I'll let everyone have a look at the rest of the notebook at their own time. I would highlight that you can do entirely the same procedure for that other noise process I mentioned. So you can also produce pulses which are robust to a miscalibration on the amplitude of your microwave drive. So say your Rabi rate isn't quite right. Once again, you can get quite significant robustness. So here we're seeing robustness with regard to the control noise on the order of about 10% compared to a primitive pulse as well. So that notebook is publicly available. You can check it. We have some new results, which I'm happy to share with you, and we're currently preparing a publication on this. So everything I just showed you then was looking at the performance of just one gate and adding some noise to verify that what we were doing was implemented right and then was robust as we expected. We then went on to basically better investigate the quality of these gates by basically what we did is we amplified the noise by just repeating the gate multiple times. And we're also doing investigations using randomized benchmarking as well. But the key result here I'm showing is, first of all, we took those amplitude robust pulses. So we did find that amplitude robustness appears to be very, very important on the IBM machine. What we did is we also took those pulses and applied it to a different machine called Valencia. So Valencia has 5 qubits available. RMOC is the single qubit device, which is publicly available. Because of our partnership with IBM, we were able to get special access to Valencia, which allowed us to check it on their 5 qubit device, which also allows us to do pulses actually much quicker as well. They give you much more access on Valencia. So what we're showing here is no artificial added noise. These is just the raw performance of our robust pulses versus their default pulses. So what we can see here is that the pulses on the machine are normally of quite a varying degree of quality. So qubit number 4, I think my face is hiding it, but it's up here. Its quality is much, much worse than qubit 0, for instance, which is their best gate, their best qubit. But when you use Q-Control's robust pulses, the effective gate error quite significantly reduces on the best gate. And also we find that the worst qubit performance becomes much more similar to the best qubit. So our amplitude robust pulses can homogenize errors in the device and also in this case actually improve their performance. The other key thing is, as I mentioned at the beginning, because all of our pulses are designed to be robust, they also are robust in between calibration steps. So when you're using these devices, things tend to drift, amplitudes tend to drift. There is also temperature shifts throughout the day. And we can see here that we did one calibrated pulse run on May 19th, and then we used that same pulse for the next 4 days. And you can see that the Q-Control pulse does start to get a little worse over the 4 days, but it still remains better than the IBM pulses that are calibrated every day. So this shows that we can homogenize errors we can homogenize performance both across the device and in time. And so that does open a lot of interesting opportunities when it comes to how you route algorithms on a device, and also allows you to get more, allows you to have more reliable results as you do them over the days, because there is an issue, there is significant challenges. Of course, you can see on May 20th, that the performance of the device was actually much better than the May 22nd. So this variability can lead to some confusion when you're trying to use IBM's machine. The last thing I just wanted to highlight is we also looked at sort of a start on the crosstalk error. So if you try to do one approach to kind of minimize crosstalk is you do gates sequentially. So each qubit you apply unitary independently. That has the penalty in that you end up going n times slower than if you're just able to run all those gates in parallel. So we had a suspicion that we were designing pulses which were robust to amplitude. So we thought that this technique would also allow us to be robust to small crosstalk errors, even on the individual gates, which can occur. And so we investigated this. So what we're doing here is showing the dotted line is the performance of the IBM's device when you do the gates in sequence. And then you can see that this significantly poorer performance occurs when you try to do the gates in parallel. So there is a relatively significant crosstalk effect. Q-Control's robust results, there is still some difference. So there is a little bit of a drop when you try and do things in parallel, but you can see it's significantly better than the drop that is on the IBM device on its own. So this extra effect allows you to also potentially improve the speed of your algorithms by running them in parallel instead of in sequence. So that concludes the majority of the content. We've still got 20 minutes of questions if anyone's interested in. And I just wanted to finish by mentioning we're continuing to expand, and we're interested in opening an office probably in Germany. There was a little bit of a delay in this because of COVID, but we're certainly looking to ramp up again throughout the end of the year. So if any of you are interested in any of the things you've heard, you're welcome to send me an email or just go to qcontrol.com and let us know about what you're working on, and we'd be happy to have another conversation. So any questions?
I guess I sort of have another question.
Mm-hmm.
So far, everything you've shown has been a closed system, and I guess piecewise constant pulses. Is there any chance that you would be able to do open systems? So, I mean, I know that differentiating through an ODE solver is difficult, but is it something you're looking into? Is it? I'm just curious.
Yeah. So I want to be careful about what I say. So just on a technicality, I wouldn't necessarily say that everything we do is piecewise constant. We have different integration techniques which can allow you to integrate smooth functions. So we can do optimizations in different, like sinusoid bases or other things like that. But that's just an aside. Yeah, the key question is open systems. So we are very interested in open systems. We have ideas on how to extend our optimizer to deal with open system dynamics. I would say that in current quantum computing hardware, often the open dynamic problem is really just horrible and boring. So if you have just a bad T1, so if your T1 time is bad because you're just leaking into the environment, there isn't a lot of control techniques you can use to help with that problem.
Okay.
But nevertheless, there are more and more exotic quantum computing hardware coming out in the market where you might be able to engineer more interesting environments. And I know once you engineer an interesting environment, there is a lot of interesting physics you can begin to explore. And so we are looking to add basically an open system feature.
Right, okay.
Yeah.
Cool. Thank you.
No problem.
Michael, I have another question.
Yep.
So regarding your last slide, I was wondering if you had any idea why sometimes actually doing the gates in parallel made them better. So that's the case, for example, in qubit 4.
Yeah, so qubit 4, qubit 4 is notoriously weird. that's all I can say at the moment. So we've been looking Qubit 4 has a variety of very unusual features. Even when you do a Rabi rate experiment, it does seem to have a different offset. It's just different. We are still investigating. We have a suspicion that there might actually be some kind of parasitic two-level system nearby, which is creating quite different exotic behavior, which we're trying to investigate. But no, I guess largely that's still a mystery to us. But yeah, all I can highlight is that Qubit 4, with a variety of different measures, also often has very odd behavior. So it's just something that we're investigating. It's certainly, I would just highlight, I just think IBM have done a great job opening their system, because it really is interesting being able to explore a device on this level. OpenPulse really gives you access to prove their device, possibly in ways that they haven't proved it before. So I really think that approach is actually quite powerful in terms of the science, which we're able to explore with their device as well. So sorry, I don't have a complete answer, but I would say it's very interesting, and I encourage everyone to have a look at IBM Q as well and investigate, because it's a really rich platform to look at a lot of new physics, I would say.
So there is a question from Marva, which I will repeat. I don't know if she has a microphone problem, but let's see. I thank you for the talk. Regarding the company itself, I see you are a pretty big team. How many people did you start with, and how fast did your team grow up?
Yeah, so we started with a team of, I think it was six people with, and at the very beginning, it was already a pretty even mix between people who had a background in quantum computing and people who had a background in developing like web software. So we grew to, I think, around 10 people in the first year and a half. And then the key thing that happened is we secured the Series A funding, which allowed us to, we had a significantly large amount of more capital then, and we were able to secure that ultimately because our first kind of product, like Opal, had a lot of traction, and it kind of showed that we could produce reliable software which was able to convey control in a new way. And then after that, I think we've scaled up to 40 in basically the last year and a half. So there's been quite a lot of hiring quite rapidly. I think we're almost 3 years old now. Just trying to keep track of the exact dates. It's been, yeah, so the venture capital funding allows you to really kind of scale up quite quickly. But we still are in a good position in that we have quite a lot of runway left to further develop our products and things. Yeah.
So I have another question.
Mm-hmm.
You focused a lot on qubits and the IBM system, but I saw on your website that you've done a bit with cold atom sensing.
Yep.
And I was just wondering if you could talk a little bit about using the different platform for a different application, so to speak.
Yeah. Let me just go back to this window. So I'll mention two things. So first of all, we also have done, Michael Biersick has a cold ion lab, which we are affiliated, well, not affiliated with, we work as an academic partner with. So all of the optimization results that have been on these superconducting devices, we've also tested with cold ion systems. And one thing to highlight there is this notebook which talks about actually 2-qubit entangling gates with ions, and we have experimental evidence. The end. Sorry. No. So yeah, this is So this is actually an experimental validation of robustness. Again, it's a very similar plot where we're trying to achieve a target state, and we can see that Q controls, robust controls, are robust to a detuning error for a significantly larger amount of detuning than a standard control pulse for a Moorman-Sorensen entangling gate with cold iron system. So just you have a look at that if you want to look at cold irons. The work we've done on cold atom sensors. So with cold atom sensors, you are typically dropping a set of atoms in the air, and the dropping of the atoms ensures that the atoms act as a great inertial reference. But the challenge is that you end up using these lasers to basically kick the atoms as they fall, and the quality of those lasers can degrade because of vibrational coupling through fibers or the mirrors on either side. So the control techniques that we've designed allow you to be more robust to those noise processes. So this is it's a theoretical demonstration with a simulation of a cold atom sensor. And here, I mean, I can skip, I'll just briefly skip to the end. So this is a theoretical demonstration of a simulation of a cold atom sensor with basically we're considering that the laser has around a 25%, which is quite significant, but a 25% instability in the amplitude. So that can be a problem if you're actually, deploying these cold atom systems on a very shaky boat or in a submarine or something. And so when you use Q controls pulses, what you actually do is you effectively improve the effective quality of your laser because you make it robust to those amplitude imperfections. And this allows you to do your quantum sensor. It allows you to capture and use more of your atoms than you normally would, which increases your fringe contrast. So here, basically, this is the fringe that you would get your interferometric fringe from your cold atom interferometer as you apply the signal being your acceleration. And you can see that the Q control pulses, when used, has a much larger interferometric sign, like fringe, which effectively means that if you're operating at this point, you'd get an increased signal because your gradient is much steeper compared to this red curve, which is just a regular pi on 2 pulse sequence. This result is a theoretical demonstration in this, or a simulation, which is shown in this manuscript. Have a look at it, all the details are there. And we're currently partnering with the Australian National University. They have a cold atom sensor research group, and we're looking to do an experimental demonstration with them. But we're also open to working, if anyone else has an interesting platform where they'd like to test these ideas, we'd be happy to talk with you as well. Does that answer your question? Do you want me to go into any more detail?
No, that's fantastic. Thank you very much.
No problem.
Other questions?
So I have one question.
Mm-hmm.
So are you also thinking about going for the multiple qubit gates or designing the pulse sequences?
Yeah, so so I mentioned that we have solutions already for cold iron systems, but for there is a notebook here which looks at a cross-resonance gate. The cross-resonance gate is the one that is deployed in the IBM machine. We're currently working through their open pulse cross-modulation techniques to get a better understanding of how it works. It's important to remember that ultimately the open pulse feature from IBM is still, it's almost at its early days for it still. So we're still learning precisely what each of their kind of controls actually do on the real system. But we have control solutions, which you can have a look at here, and will work, theoretically have been demonstrated to work with crosstalk to be robust to crosstalk on a cross-resonance gate, and we're looking at deploying them now through open pulse as well. So the results on IBM are a work in progress, but there are already results proven for cold iron systems, which are all available here online as well.
Okay, thanks.
Any last question? Well, I don't hear anyone, so Michael?
Oh, sorry, actually, I have a question.
Oh, okay.
So my question regards this stack, and it seems like you investing some time in building up a large part of the stack. And I'm just wondering, since you have a strong collaboration with IBM and the presence of a large part of the stack also in the QuSCo code, if you are trying to avoid overlaps, or if they're meant to be two separate ways to implement the stack, what's happening there?
Yeah, I think maybe this maybe this diagram kind of gives a wrong impression. We're definitely that's something we're very conscious of, let's say. So we really aim to be specialized at improving deploying quantum control solutions, and really deploying them just above the physical layer. So IBM is a good example. So IBM has been actually quite open, and this Open Pulse is a good example where they were quite willing to open their hardware level at a lower level to that pulse level control, because they want to have a dynamic research and business community where people can contribute their own solutions at that level. So IBM has definitely shown an interest in not necessarily as opening more the part of their stack between the actual, let's say, quantum circuit and what pulses are realized on their devices. So we fit quite nicely there. In terms of the top level, don't have any. We have some interest with Black Opal in making quantum control more accessible to more people, but we're not particularly interested in creating another language for quantum computing. So QuSCo obviously is great, and there's many other great languages for programming quantum computing. We're not aiming to make a new language to do something like that. Our aim is more that once you've picked a language, you got your program, then DevKit is more about sitting beneath that layer and taking a circuit, basically transpiling it to run that circuit with the right pulses so that you get the best out of the device you're running it on. We largely think it's a nice situation where we can be quite compatible with everyone else. Algorithm developers can make their algorithms more and more efficient in terms of number of gates. We can then take those gates, do drop-in replacements and minor alterations on the circuit level to really improve the performance of that algorithm. And then other things like the actual physical hardware producers can make better and better devices. And as I mentioned, there's always going to be some things that controls can't solve, like we can't do a lot for just a basic T1 time issue where you're just losing excitation into an environment. Like that really is something that the hardware producers have to do a better job on. And we're really able to just add that extra bit, the extra enabling layer when it comes to these T2 times and these dephasing errors and things like that. So yeah, we aim to touch a lot of people who are quantum engaged at either like the early level, the algorithm level, or making hardware. We want to be friendly with everyone and provide products to everyone, but we want to do that in a way that's compatible with other products in the quantum space as well. That's the key.
Thank you.
No problem.
Any more questions? Don't be shy.
Can you talk a little bit about what led you to Q-Control as opposed to, for example, a larger company or a more academically oriented career?
Yeah, so I was a lecturer before this. I was an academic. I was working at an Australian university, UNSW, in Canberra. And yeah, I guess at the time, I've always been a little bit more driven as like a quantum technologist. So I've always been really, really keen to kind of contribute to making real hardware work better. Academia is like a very rewarding career in the sense that you have a lot of independence and a lot of free thought, let's say. But there is a strong emphasis on doing novel things which are new. And I was finding myself kind of more keen to contribute on the business side of things and get things that we do have working better now. And then just coincidentally, around that same time, I've had a relationship with Micheal Hush before. We were kind of in the same Australian research community on quantum control. And when QControl was funded, it just seemed like a no-brainer for me. So I basically just completely jumped out of academia and went straight into this role at QControl. And for me, it's just been, what I like about the startup aspect of things is you get to, first of all, you get to see every part of a business. So I've been there since basically day 10 or something at QControl. So I've seen everything from all of the different moving parts of the business kind of build from the ground up, which I find fascinating, kind of learning how a business works. And also the nice thing about a startup is it's often easier to create a change quicker. So everyone at the company has direct access to our CEO, Micheal Hush. And that's also been really nice about being in a startup, is that you can get idea to reality very, very quickly and respond to what's going on in the market or a great new idea that's come up from someone inside the company. So I guess, yeah, I think that it's a very exciting time to be in the quantum computing industry. There is a lot of opportunity. There is a lot of uncertainty as well. The hardware, there's a lot of difficult problems to solve with the hardware to get it to that point of particular, let's say, cracking RSA or encryption. We are very, very far away from that. But nevertheless, if you're very interested in kind of combining software, your quantum control theory, and doing that in a way, in a business-oriented way instead of, let's say, a novel academic way, it's a really great time to kind of pursue a career in the quantum industry that's kind of developing now.
Great, thank you.
Okay, I guess we can accept one more question if there is one, and then we let Michael go home because there is 6 p.m. And so, okay, seems like we have exhausted all the questions. So Michael, thank you very much for your time and for the presentation. I will share, if you don't mind, with the students your contact, so maybe some of them may be interested into talking to you for this expansion into Germany, for instance, or maybe if they have additional questions that they didn't dare to ask on the recording. And thank you very much again, and thank you very much to everyone that took the time to join at this morning session. So
thanks again. Thanks for the great questions as well, by the way. That was fantastic. And yeah, feel free to contact me afterwards. Thanks again.
Bye.
Bye.
Goodbye.